energy, energy transfer, and general energy analysis. This topic introduces the broad scope of energy, energy transfer, and energy analysis in thermodynamics. Energy is treated as a central concept that connects all physical and engineering processes. The discussion emphasizes how energy is stored, transferred, and converted from one form to another. The approach is systematic and based on energy balances. This chapter forms the foundation for understanding the first law of thermodynamics.
Lesson Plan Thermodynamics I. The course structure is arranged progressively from basic concepts to more advanced energy analysis. The chapter sequence shows a logical flow from definitions to closed and control volume systems. Each chapter builds on the previous one to strengthen understanding. The energy chapter serves as a bridge between fundamentals and system analysis. This roadmap helps students see where the energy topic fits in the whole course.
Learning Outcome. The learning outcomes emphasize a comprehensive understanding of energy concepts and their forms. Students are expected to distinguish between heat, work, and internal energy conceptually. The first law of thermodynamics becomes the main tool for system analysis. Efficiency concepts and environmental implications are also introduced early. Therefore, the learning is not only technical but also contextual.
Refrigerator in a sealed room, much like a refrigerator, removes heat from its interior and releases it to the room, while the electrical energy consumed by the compressor is also converted into heat. In a sealed room, no energy actually leaves the room system. As a result, the total energy inside the room increases. The average room temperature will rise, not decrease. This example emphasizes the importance of considering the overall energy balance.
Fan in a sealed room. A fan only circulates air without removing thermal energy from the room. The electrical energy supplied to the fan motor is eventually converted into heat. In a closed system, this added energy increases the room temperature. There is no mechanism to reject energy outside the system. This example shows that not all electrical devices can provide a cooling effect. Check your understanding. Number 1. This question tests the understanding that electrical energy in a fan does not disappear but changes form. The focus is on energy conversion, not on the cooling sensation felt by humans. In thermodynamic analysis, the energy balance of the system is what matters. All input energy must appear in another form. This reinforces the principle of energy conservation. Energy transfer in power generation. Nuclear energy is converted into thermal energy, then into mechanical energy, and finally into electrical energy. This process shows that energy often goes through several conversion stages before being used. During transmission, energy also appears in magnetic and kinetic forms. In homes, electrical energy is converted again into useful forms. This chain of conversions is a hallmark of modern energy systems. Macroscopic energy of motion. Kinetic energy increases as the vehicle speed increases. Potential energy increases when the vehicle is at a higher elevation. The total macroscopic energy is the combination of velocity and elevation contributions. This concept is important for analyzing real moving systems. This approach does not consider the microscopic structure of matter. Steam flow in a pipe. The mass flow rate depends on the cross-sectional area, density, and flow velocity. The energy flow rate is proportional to the mass flow rate and the energy properties of the fluid. The average velocity becomes a key parameter in energy transport. A flowing fluid always carries energy with its mass. This is very important in control volume analysis. Microscopic energy forms. Microscopic energy comes from molecular translation, rotation, and vibration. In addition, electron motion and spin also contribute to energy. Even atomic nuclei contribute through nuclear spin. These forms are not directly visible, but affect the thermal properties of matter. The internal energy of a system comes from the accumulation of these microscopic effects. Internal energy components. Internal energy consists of several main components that originate from the microscopic structure of matter. Sensible and latent energy are related to molecular motion and phase changes. Chemical energy is stored in the bonds between atoms and molecules. Nuclear energy comes from forces within the atomic nucleus. All these components together form the total internal energy of a system.
Answer C. Nuclear energy. Explanation of why other answers are wrong. A. Sensible and latent energy. These are related to molecular motion, sensible energy, and phase changes, latent energy, not atomic nuclei. B. Chemical energy. This energy is stored in atomic bonds between molecules, not derived from the forces within atomic nuclei. D. Kinetic energy. Kinetic energy is the energy of motion and unrelated to the forces within atomic nuclei. Kinetic energy forms. Kinetic energy can appear in microscopic and macroscopic forms. The random motion of molecules cannot be used to perform organized mechanical work. In contrast, organized water flow can rotate a turbine and produce work. This difference shows that the orderliness of motion is crucial in energy utilization. Not all kinetic energy has the same usefulness. Nuclear reactions and energy. Fission reactions split heavy nuclei, such as U-235, and release a huge amount of energy. Fusion reactions combine light nuclei, such as hydrogen, and also produce large amounts of energy. Both processes involve the conversion of mass into energy. This is why nuclear energy is much denser than chemical energy. This principle is the basis of nuclear power plants and fusion research. Mechanical energy in fluid flow. The flow of fuel from the tank to the car is driven by mechanical energy. This process does not involve significant heat transfer. The energy is transferred purely through mechanical work. This example shows that not all energy processes are related to heat. In many engineering systems, mechanical work is the main mechanism of energy transfer. Hydraulic turbine energy. Water flowing from a higher elevation carries potential energy that can be converted into mechanical energy. The turbine converts this energy into shaft rotation. The generator then converts it into electrical energy. The amount of power produced depends on the head or pressure difference. This shows the direct relationship between flow conditions and energy production.
Check your understanding number 3. This question emphasizes the energy conversion chain from mechanical to electrical. The turbine does not produce electricity directly, but through a generator. This clarifies the role of each component in a power system. This understanding is important for efficiency analysis. Each conversion stage always involves some energy losses. Closed system energy transfer. In a closed system, the mass of the system remains constant during the process. Energy can cross the system boundary in the form of heat or work. The change in system energy is completely determined by these energy interactions. No mass enters or leaves the system. This model is very important in many basic thermodynamic analyses. Heat transfer and temperature difference. Heat transfer occurs only when there is a temperature difference. The larger the temperature difference, the greater the heat transfer rate. If the temperatures are the same, no heat flows. This example shows that temperature is the driving force for heat transfer. This concept is the basis of all heat transfer analysis. Heat transfer in a system.
Thermal energy is stored in the system as part of its internal energy. Heat is defined only when energy crosses the system boundary. Once the energy enters, it is no longer called heat, but becomes internal energy. The system boundary plays a key role in this definition. This concept helps distinguish between system properties and energy interactions.
Adiabatic system characteristics. An adiabatic system does not allow any heat transfer with the surroundings. The change in energy within the system can only occur through work. Thermal insulation serves to prevent heat energy leakage. Such processes are often used as ideal approximations in engineering analysis. This concept is very important in compressors, turbines, and nozzles.
Heat transfer relationships. The total amount of heat depends on the system mass and the duration of the process. The heat transfer rate indicates how fast energy is transferred per unit time. The specific heat per unit mass helps compare energy distribution in the system. These three quantities are related but have different physical meanings. Understanding these differences is important in energy calculations.
Answer B. Rate of heat. Explanation of why other answers are wrong. A. Total heat. Total heat refers to the amount of heat transferred, Q, depending on the system's mass and time duration, not the rate of energy flow. C. Specific heat. Specific heat, Q, represents heat per unit mass, describing energy distribution within the system, not the rate. D. Latent heat. Latent heat is related to phase changes, not energy flow per unit time. Caloric theory in heat transfer. In the past, heat was considered an invisible fluid called caloric. This fluid was believed to flow from a hot object to a cold object. This theory helped explain heat phenomena at that time, even though it was incorrect. As science developed, this concept was replaced by the energy theory. This example shows how scientific understanding evolves over time. Work relationships. Total work represents the amount of energy transferred during a process. Power indicates how fast this work is done. Specific work represents work per unit mass of the system. These three quantities provide different ways to view mechanical energy interactions. These relationships are very important in the analysis of machines and engineering equipment. Heat and work directions. Heat and work can enter or leave the system, depending on the process. Positive and negative signs are used to indicate the direction of energy flow. The system boundary becomes the main reference for determining the sign convention. This concept helps avoid confusion in energy balance equations. Consistency in using signs is very important in calculations. Path functions in processes. Properties such as volume depend only on the initial and final states of the system. In contrast, work and heat depend on the path taken by the process. Two different processes can produce different amounts of work, even if the initial and final states are the same. This shows that work and heat are not system properties. This concept is fundamental in thermodynamics. Electrical power relationships. Electrical power can be expressed as the product of current and voltage. Power can also be written as the square of current times resistance. In addition, power can be expressed as the square of voltage divided by resistance. These forms show the basic relationships among electrical quantities. These equations are very important in the analysis of electromechanical systems. Check your understanding. Number 5. This question tests the understanding of alternative forms of the electrical power equation. The focus is on the relationship between voltage, current, and resistance. Different equation forms are often used depending on the available data. This understanding is important in circuit and electrical equipment analysis. Incorrect substitution can lead to power calculation errors. Work and motion.
Work is proportional to the applied force and the distance moved. The force must be in the same direction as the displacement to perform work. Work is one of the main mechanisms of energy transfer. This concept originates from classical mechanics and is widely used in thermodynamics. With this concept, energy can be directly related to force and motion.
Rotating shaft energy transfer. Rotating shafts are widely used to transmit energy in mechanical systems. Engines transfer power to the load through shaft rotation. The system efficiency is strongly influenced by the shaft design and condition. Energy losses can occur due to friction and mechanical imperfections. This concept is very common in pumps, turbines, and machines. Shaft work and torque. Shaft work depends on the applied torque and the number of revolutions. The larger the torque and the greater the number of revolutions, the larger the work transferred. Torque is a measure of the tendency of a force to cause rotation. This relationship connects the concept of work with rotational motion. This is the basis for power analysis in rotating systems. Spring elongation and force. A spring elongates when a pulling force is applied. The amount of elongation depends on the magnitude of the applied force. The spring provides a restoring force in the opposite direction of the applied force. This relationship is the basis of elastic behavior. This concept is important in many mechanical and structural systems. Linear spring displacement. In the linear elastic region, the spring displacement is proportional to the applied force. If the force is doubled, the displacement also doubles. This relationship is known as Hooke's law. As long as the elastic limit is not exceeded, this relation holds. This simplifies energy analysis in spring systems. Answer C. The displacement doubles. Explanation of why other answers are wrong. A. The displacement decreases. Incorrect, because increasing the force cannot decrease the displacement in a spring obeying Hooke's law, linear elasticity. B. The displacement remains unchanged. Incorrect, because displacement is directly proportional to the applied force. Increasing force will increase displacement. D. The displacement triples. Incorrect, because the relationship is directly proportional, so doubling the force results in double, not triple, the displacement. Solid bars and elasticity. Solid bars can also behave like springs when subjected to a force. The deformation depends on the magnitude of the force and the material properties. As long as it is within the elastic limit, the bar will return to its original shape. This concept is important in strength of materials analysis. Elastic energy can be stored in this deformation. Liquid film stretching. A liquid film can be stretched by moving a wire in a U-shaped frame. A pulling force appears due to the surface tension of the liquid. The larger the surface area created, the more work is required. This process shows that energy can also be stored in surfaces. This is an example of work associated with surface effects. Energy and elevation. Lifting an elevator increases its gravitational potential energy. The motor performs work against the weight. The work done by the motor equals the increase in potential energy. This concept links mechanical work with changes in potential energy. This principle is very common in lifting systems. Energy transformation. Potential energy can be converted into kinetic energy when an object moves. As long as there is no energy loss, the total energy remains constant. At the highest point, the energy is entirely potential energy. During motion, the energy gradually changes into kinetic energy. This is a direct illustration of the law of energy conservation. Heat transfer to potato
The energy of the potato increases because it absorbs heat from the surroundings. The amount of energy change equals the amount of heat received. This process continues until thermal equilibrium is reached. No work is involved in this process. This example emphasizes the direct relationship between heat and the change in internal energy. Check your understanding number 7. This question emphasizes the concept of thermal equilibrium as the final condition of heat transfer. As long as there is a temperature difference, heat transfer will continue. When the temperatures become equal, there is no more driving force for heat transfer. This is a basic concept in all thermal processes. This understanding is important to determine the final state of a heating or cooling process.
Net heat transfer. The change in system energy equals the net heat transferred into the system. Heat input minus heat output determines the sign and magnitude of the energy change. If there is no work, then heat becomes the only mechanism for energy change. This concept simplifies the analysis of many thermal systems. This is a direct form of the first law of thermodynamics. Work and energy in adiabatic systems. In an adiabatic system, there is no heat transfer with the surroundings. Any change in energy must come from work. If electrical work is supplied, the internal energy of the system increases. This shows that work can directly change the energy state of a system. This concept is very important in compressors and pumps. Shaft work in adiabatic systems increases the internal energy of the system. Since there is no heat transfer, the entire energy change comes from work. This clarifies the role of mechanical work in changing the system state. Such analysis is often used in turbines and compressors. This relationship is a direct application of the first law. Boundary work in adiabatic systems. Boundary work done on an adiabatic system also increases the system energy. There is no heat contribution in this process. All energy changes can be directly related to boundary work. This shows that different forms of work have the same effect on system energy. This approach simplifies the energy balance. Answer B. Boundary work input. Explanation of why other answers are wrong. A. Heat transfer from the surroundings. Incorrect, because in an adiabatic process, there is no heat transfer. Energy change arises solely from work. C. Internal chemical reactions. Incorrect, because the problem specifically attributes energy change to boundary work, not chemical reactions. D. Thermal radiation exchange. Incorrect, because thermal radiation is not a factor in an adiabatic process where the energy change is due solely to work. Energy change in systems. The total energy change of a system comes from the combination of net heat and work input. The net heat provides part of the contribution, and the shaft work adds the rest. The sum of both equals the total energy change. This is the general form of the energy balance equation. This approach applies to many types of systems. Stationary system energy. If there is no change in velocity and elevation, then there is no change in kinetic and potential energy. In this condition, the total energy change comes only from internal energy. This greatly simplifies the analysis of many stationary systems. This assumption is often used in tanks and closed vessels. Thus, the focus of analysis can be narrowed. Energy change in control volume. In a control volume, energy can enter and leave with mass flow. In addition, heat and work can also cross the system boundary. All these contributions must be included in the energy balance. This makes control volume analysis more general than closed system analysis. This approach is very important in the analysis of turbines, pumps, and heat exchangers. Energy balance in a cycle. In a complete cycle,
the system returns to its initial state. Therefore, the total energy change over one cycle is zero. The net heat input must equal the net work output. This is the basic principle of heat engines and refrigeration cycles. This concept is very important in thermodynamic cycle analysis.
Check your understanding number 9. This question reinforces the relationship between net heat and net work in a cycle. Since the system returns to its initial state, there is no net change in total energy. Therefore, the net heat input must equal the net work output. This is a characteristic of all heat engines and refrigeration machines. This concept is a simple form of the first law for cyclic processes.
Water heater efficiency shows how much of the input energy is actually utilized. Electric heaters generally have higher efficiency than gas heaters. However, this efficiency must be understood in the context of the overall system. The efficiency difference reflects differences in energy losses. This concept is important in evaluating everyday energy technologies.
Heating value of gasoline. The heating value of a fuel indicates the energy released per unit mass during combustion. Gasoline has a high heating value, making it suitable as a vehicle fuel. This energy is released in the form of heat and combustion products. Reference temperature conditions are important for comparing heating values. This concept is very important in combustion system analysis.
Lighting system efficiency. Lighting efficacy shows how efficiently electrical energy is converted into light. Old technologies such as candles and oil lamps are very inefficient. Modern lamps such as LEDs are much closer to the theoretical limit. This shows how technological progress improves energy utilization. This example connects energy efficiency with everyday life.
Compact fluorescent versus incandescent. Energy-saving lamps can provide the same level of illumination with much less power. This means less energy is wasted as heat. This comparison shows the importance of choosing the right technology. Energy savings can be achieved without sacrificing lighting quality. This concept is important in energy efficiency policy.
Answer B. They provide equivalent brightness while consuming less power. Explanation of why other answers are wrong. A. They use the same power but emit brighter light? Incorrect, because compact fluorescents consume less power while providing equivalent, not brighter, light output compared to incandescent bulbs. C. They consume less power but compromise on light quality? Incorrect, because compact fluorescent lamps combine energy consumption without compromising light quality. D. They use more power to produce equivalent brightness? Incorrect, because compact fluorescents are specifically designed to use less power for the same level of brightness.
Energy costs for cooking. Different cooking appliances have different energy costs for the same task. These differences come from efficiency and heat transfer mechanisms. The microwave shows the lowest cost because it heats the food directly. This example shows that efficiency directly affects operating cost. Technology choice influences household energy consumption.
Cooking appliance efficiency is determined by how much energy actually reaches the food. If the efficiency is 60%, it means a large portion of energy is still lost to the surroundings. These losses are usually in the form of useless heat. This concept is identical to the efficiency definition in other engineering systems. This emphasizes the importance of good thermal design.
Fan mechanical efficiency. Fan mechanical efficiency indicates how much of the input power is converted into mechanical energy of the air. Some power is always lost due to friction and internal losses. A high efficiency value indicates good design. This concept is very important in machine selection and evaluation. It also shows that no machine is perfectly efficient. Turbine generator efficiency. The overall efficiency of a turbine generator system is obtained by multiplying the efficiencies of each component. The fluid mechanical energy is first converted by the turbine into shaft mechanical energy. The generator then converts it into electrical energy. Each stage has its own losses. Therefore, the overall efficiency is always lower than the efficiency of each individual component.
Check your understanding. Number 11. This question emphasizes that the overall efficiency of a combined system is not added, but multiplied. This is often a source of mistakes in calculations. Each component contributes to the reduction of the overall efficiency. This concept is important in analyzing energy conversion chains. This understanding is crucial in power system design.
Environmental impact of energy. Energy conversion processes often produce pollutants that harm the environment. Fossil fuel-based power plants are one of the main sources of emissions. These impacts include health problems and climate change. Therefore, environmental aspects must always be considered in energy planning. Energy is not only a technical issue, but also a social one.
Vehicle emissions and pollution. Motor vehicles are the largest contributors to air pollution in many countries. Exhaust gases such as nitrogen oxides, carbon monoxide, and hydrocarbons are very harmful. These emissions contribute to smog and respiratory problems. This problem is directly related to energy consumption in the transportation sector. The solution requires both technological and policy approaches.
Ground-level ozone and smog. Smog is formed from reactions between hydrocarbons and nitrogen oxides under sunlight. Ground-level ozone is the main component of smog. This phenomenon usually appears on hot and calm days. The impact is reduced air quality and health problems. This shows the close relationship between energy, chemistry, and the environment.
Acid formation in atmosphere. Sulfur oxides and nitrogen oxides react with water vapor in the atmosphere to form acids. These acids then fall to the ground as acid rain. The impact is very damaging to ecosystems and buildings. The main source of these pollutants is fossil fuel combustion. This is a direct example of the environmental impact of energy conversion.
Check your understanding. Number 12. This question reinforces the term for rain that contains strong acids formed by atmospheric reactions. The focus is on the relationship between emissions and environmental impact. This concept often appears in discussions of energy and the environment. This understanding is important to see the long-term consequences of energy technologies. The term has become a common part of environmental literature.
Greenhouse effect. The Earth's surface absorbs solar radiation and emits infrared radiation. Greenhouse gases absorb and re-emit this radiation, trapping heat in the atmosphere. This process causes a rise in global temperature. The greenhouse effect is a natural physical phenomenon, but it is intensified by human activities. This is a major issue in modern energy policy.
Vehicle CO2 emissions. Each vehicle produces a very large amount of CO2 emissions every year. Fuel consumption is directly related to the amount of emissions released. Every liter or gallon of fuel burned produces CO2. This shows the direct link between energy, mobility, and climate change. Transportation becomes a key sector in decarbonization strategies.
Renewable energy benefits. Renewable energy, such as wind, produces no pollutants during operation. This source is sustainable because it does not run out. The use of renewable energy reduces dependence on fossil fuels. It also helps reduce greenhouse gas emissions. Therefore, renewable energy becomes a pillar of the global energy transition.
Answer C. It helps combat climate change by reducing reliance on fossil fuels. Explanation of why other answers are wrong. A. It increases reliance on fossil fuels for backup energy. Incorrect, because wind energy reduces reliance on fossil fuels rather than increasing it. B. It produces pollutants and greenhouse gases during operation. Incorrect, because wind energy generates no pollutants or greenhouse gases during operation. D. It is a finite energy source that needs constant replenishment. Incorrect, because wind energy relies on an endless, sustainable natural resource.
References. The references show that all figures and main concepts are taken from a standard thermodynamics textbook. This confirms that the material is based on a credible scientific source. This book is a main reference in many engineering universities. Using standard references ensures consistency of concepts and notation. It also makes it easier for students to study further independently.